Thank you, Alex. Thank you very much. Title's very simple. Seeing molecules with entropy. And I'd like to jump with you exactly to what exactly this means. It's kind of clear. I'll skip on it, but we can comment on it later. So, as the title says, it's about seeing. And seeing molecules is not something very straightforward, right? But the thing is, whenever in labs you try and figure out what the molecular structure of something is, as it turns out, you shine light on top of it, and then you get something back, and then you use that to try and figure out exactly what the molecule is. And of course, you're looking at molecules, and you're using a transformer to do that. It's not exactly a transformer as pictured here. And so, to do this, I'll be very quick, and I'll show you exactly what it's about. But there's three things now. So, as I was saying before, photons are collections of atoms, right? And as it turns out, when you shine lights on top of them, they vibrate. And this vibration depends on the structure of the molecule and of the light that you're shining on top of it. And so what happens is, looking at what you get back, so the light that bounces back from the molecule, you can kind of figure out what it is. So there's quite a bunch actually of different ways of doing this. It's called spectroscopy methods. And they're actually used very often by chemists, right? Now, something that seems completely unrelated. Let's look at a transformer. Everybody knows what that is, right? Yeah. Decoder only, so the bottom part is basically what an LLM is, right? So how it works, take an input, whatever input, we just saw it with NAND. And then the output is a distribution. Distribution means there's a vocabulary of tokens, you have a distribution of all possible tokens, right? Of the probability assumptions. Now, as it turns out, molecules can easily be represented as strings. And so it's tokens, right? And so probably you're starting to see where I'm going. There's a problem with this representation. It's very fragile, right? So, for example, when you're talking to a reasoning model, R1, right? It uses a bunch of tokens to try and backtrack if it makes a mistake. If you talk to R1, you see overthink all the time, right? And it's like, oh wait, let me go back to this concept, that other concept. You can't do this when the transformer is not outputting language tokens, but it's outputting tokens in smiles, which basically are atoms in the molecule, right? Because you sample the wrong atom, and you're gone. Like, the atom is there, and it's going to be in the context, and it's going to be the wrong molecule, right? And so we need to try and make this output space, which is very fragile or robust. Enter something that is not showing up for some reason. Okay, wait a second. I think it's the connection. Why the hell is this not showing? Okay, I'll show you from here. It's there. Enter Entropix, which was quite a phenomenon on Twitter. And it's about basically using how the model is uncertain, so it outputs a distribution, right? And this distribution has an entropy. So entropy means how collected are the probabilities in the output distribution, right? So they could be very sparse, so the entropy could be very high, or entropy would be very low, right? And the idea is, okay, you use this information to try and steer the model. So if the model doesn't really know what's going on, you better try and give it a nudge, right? And so what happens is, Entropix finds basically a strategy for each of these quadrants. So basically, if you very high entropy, you don't know what you're doing. In regular language, you use tokens like wait. So you tell yourself, okay, wait, let me go back and figure something out. And then, if you're very sure, you sample the token. If you have a few tokens all at the same level, you branch out, right? And of course, you cannot do that in molecules because there's no weight token, right? You cannot circle back. And so something else I want to introduce you to is layer looping. You're not even saying this? Okay, I don't know what's going on. But this will do. The idea is, okay, what you can do is you can pre-train a model, a transformer model, to loop its inner loop. So instead of inserting a weight token when you do not know what you're doing, you're telling the model, okay, if you loop more layers inside of your network, you can get smarter, right? So the output of your prediction is going to be better. And so let's go back to the chart before, which you cannot see for some reason. Okay. You cannot even see. Okay, I'll describe it to you, but the idea is when you're very high entropy, the decision that you take, so when you're risking getting the token wrong, the decision you take is you actually loop more layers, and so you do so-called latent test time compute. And so this is the analogous test time compute to the test time compute that you do in token space for reasoning models like R1. And so why are we talking about this? Because chemists, as I was saying before, take spectroscopy techniques multiple, so it's multimodal task, and try to figure out what the molecules in stuff are. It's all they do. It's all many chemists do, actually. So what I've built in my research at PhD student is a transformer model that takes multiple inputs, so multimodal input, and then uses decoding techniques to decode the molecular structure of the stuff you're looking at. Okay? And so, as it turns out, if you use these sampling techniques, it's very early results, but take it for granted. It works pretty well. And now we're going to see a very quick demo. I don't know how far I'm going to okay. So we're going to do a couple of things here. Oh, I've heard it. All right, let's see if it's tricky. So the checkpoint that I'm loading here is actually a very early checkpoint because I have the genius idea of trying a new architecture right before coming here. So people who know me know this. And so it's not going to be very good at predicting, but you can see kind of how it works. And it's going to get quite somewhere, right? And of course, the one thing I'm going to sample is not going to work. Right, I'm doing it right. So what we've done now, get random sample, is basically we've taken a random sample from the data set, a test data set that we're training this on, we've tested this on, and we've given the spectrum, so the light information that we saw before, to the model. And as you saw, the model slowly constructed the molecule, and actually the reference molecule is very close to what is seen there, right? It's not exact, but there's metrics to kind of figure this out. And this is the model not using the actual Entropix decoding, right? So this is just base model getting stuff wrong and then forgetting about it, like in context. We can run this again. I will not run this again because I don't have enough time. So what I want to show you is a couple more things, which is we're gonna compare this with some more regular test time compute that is done usually in molecules, which is beam search. If you work with LLMs, you know, beam search is just take a beam of outputs from the distribution, just string along with top K outputs and measure them. And it's not opening up for some reason. Okay, there's another bunch of. And so what we're going to see is, hopefully, if you run this enough times, you're going to see that on average, this is invalid for Entropix and very embarrassing. But on average, what comes out on the right, now again, this is very embarrassing because it's again wrong. But if on average, what comes out on the right is better than what comes out on the left. Now, it's the case in this, here it's random because I'm sampling sample by sample. It's hundreds of thousands, so it might sometimes happens that one is better and the other is better. And there's a cool way to visualize this because I built another radio app. Because, no slides allowed in ASMR. And I don't remember what its name is. It kind of visualizes the difference between beam search and Entropix. So what you're going to see is beam search basically goes, here it is. You're going to see on the left, I'm going to get a random sample again. On the left is going to be beam search. And as we go further, beam search basically doesn't care too much what the output distribution is. And instead, on the right, you have Entropix, And you can see from the color of the nodes that each has its own strategy that it's coming up with to better steer the model towards something that makes more sense based on what the model thinks, right? And so if you go ahead, you can see they have a very different kind of way of unfolding and rolling out their tokens. Okay? And this was it. Thank you very much for your attention.